Hello, this is Jake Abbott. Today in this video we're going to be talking about similarity transformations. So a similarity transformation, we're referring to square matrix functions. So we're talking about things that look like this. We're saying we have some vector y and that's equal to some matrix A times x. And this is a function. It's a function that takes in a vector x, which is some n by 1 thing, and it multiplies it by this n by n matrix and then spits out another n by 1 thing. So yes, it's a linear mapping between a vector to a vector, but you can think of it like a function. So it's mapping x that belongs to this set Rn to y that also belongs to this set Rn. And in general, functions don't have to map Rn to Rn, but the ones we're talking about are going to do that. So we have already seen that we can express this vector x with respect to any basis, and that basis is represented by some matrix Q, which is this like n by n thing. And if we do that, then we say that x, this vector x, we can represent it with respect to this basis Q through these basis parameters, which we called this x tilde. And so if you remember, Q is a basis set where it's an n by n thing, so it has n columns, and each of its columns are a vector, and those columns are all linearly independent from each other. So we have n linearly independent vectors, and we found out that any n linearly independent vectors forms a valid basis set for this space Rn. So, and then once you've picked those columns, the values in x tilde are just the multiples of the columns to basically make this vector x. So we called x tilde the representation of x with respect to this basis Q. So there's nothing special about this vector x, so this is true of all vectors in this space. So since y is also in Rn, we can say, well, we can express the vector y with respect to this new basis just as well, and let's call its representation with respect to that basis y tilde. So now we have this function here, and the question is, how do we map this function if we had this function that was written with respect to some original basis, and now we want to write it with respect to this new basis Q? And I think the kind of maybe, somewhat obvious thing to try is to say, well, maybe y tilde is equal to a x tilde. So I've mapped my x into this new space, this new basis set, and it's going to result in my y mapping to this new space. But it turns out this is not true in general. It might be true on occasion if you have some special Q, but in general this is not a good mapping. So the question is, if I have a function like this and I want to represent this function in this new basis where all my vectors are described differently, how do I do it? And so you go back to kind of just first principles. You don't make an assumption here. You just start plugging in the things you know. So we know this and we know these two things. So let's start plugging those things in. So we have that y is equal to ax, and then we have that y is q times y tilde, and x is equal to q times, well, that's a q, times x tilde. And then assuming that q is invertible, we can multiply the left side and the right side by q inverse. So I'm going to do that explicitly so you can see exactly what I'm doing. And if I'm multiplying the left side of this by q, I must multiply the left side of this by q inverse. So like this. And then this now forms the identity matrix, and I'm left with y tilde is equal to q inverse a q x tilde. And so this whole matrix Q inverse AQ is my sort of Q tilde. So, or sorry, that's my A tilde. A tilde. So now I have this new function that y tilde is equal to A tilde x tilde. So it's not only that I map my vectors x and y into this new basis, but I actually have to think of my matrix A as a function being mapped into this new basis. And while you map vectors by just multiplying by q, the way you map functions is you have to pre and post multiply by q and q inverse in this way. And this is the right way to think about it. So in doing this, I had to make this assumption that q inverse even exists. So for Q inverse to exist, we know it has to have a determinant that is not equal to 0. And so the question is, does Q always exist? And the answer is yes, Q inverse always exists. And the reason it exists is because Q is a basis set. So Q has n linearly independent columns, and if it has n linearly independent columns, then it has full rank, which means it has a non-zero determinant. So just the very fact that Q is a basis set means that Q inverse always exists. So this will always exist as we do this mapping. So let's do an example, and let's consider something like this. So let's first start with like a basis, a very simple orthonormal basis set, like the kind we're typically used to thinking about, where I draw this as a nice horizontal line and this is a nice vertical line. And let's call this I1. And so that equals, in this world, it equals 1, 0. And let's call this I2. And that equals 0, 1. And this is like, we see this basis set so often that it's almost like we assume it's how the world has to work. Like x is horizontal, y is vertical. But it's an arbitrary choice. And we have some vector. Let's draw a vector like this. Like this. And let's say this vector is the vector x that we're interested in, and it's the vector 2, 2 expressed in this basis set. So I go 2 over and 2 up, and that's that. But now we're going to question this idea, is this the only basis set we could have represented this with respect to? So let's draw ourselves, to keep things simple, another orthonormal basis set. So let's draw one that looks like this. So here it's still going to be a length 1 vector like this, and a new length 1 vector like this, and they're perpendicular to each other, just like these were perpendicular to each other. And let's call this vector J1 and this vector J2. And they're still orthonormal, so they're orthogonal, and they're normal, meaning length 1. And so this length 1 vector in this direction is going to look like 1 over square root of 2 and 1 over square root of 2. So I go 1 over square root of 2 up, 1 over square over, and 1 over square root of 2 up, and the hypotenuse is length 1. And then this vector over here, J2, I'll write it out. J2 will be this vector minus 1 over square root of 2 and 1 over square root of 2. So this J set of vectors is also a completely valid basis set. And if we wanted to write this vector x with respect to this basis set, we wouldn't get the numbers 2, 2. I mean, the way we got the numbers 2, 2 with respect to basis set 1, I'll put a little sub 1 here, is that we went 2 in the I1 direction and then 2 in the I2 direction. But clearly this vector x now is, in this new basis set, is all in the J1 direction and it's none in the J2 direction. So we're going to get a different representation. So rather than just trying to figure this out explicitly without utilizing the math and just using brute force, let's use the equations that we know. So let's write this new basis set as Q, and its columns are the basis vectors. So its first column is 1 over square root of 2, 1 over square root of 2, and its second column is minus 1 over square root of 2, 1 over square root of 2. So I've just formed this mapping Q, which its columns are the basis vectors, and now I'm going to utilize these equations that say that x is equal to qx tilde. So I'm going to figure out what is the representation of my vector x, which I already know is 2, 2. What is the representation of that vector with respect to this new basis set? And since I know this inverse exists, I can also say, well, okay, if I want to solve for the representation, that's equal to q inverse times x. So I already know x, and if I solve for q inverse, then I can now find its representation. So that makes sense. So we need to do the inverse of a 2 by 2 matrix, which we can actually figure out. And the way we do that is we say this is equal to 1 over the determinant of q. This formula doesn't work for all matrices, just 2 by 2 matrices. And then the way that you, let me just do a little quick tutorial here. If I have A equals A, B, C, D, the way I find A inverse is I go 1 over the determinant of A, and then the matrix I multiply, and this only works in the 2 by 2 case, is I swap the diagonals, so I put D here and A here, and then I minus the off diagonals, so I put minus B and minus C. So that's really easy here. So the determinant of Q, or Q inverse, is going to be the determinant of Q times this matrix where I swap the diagonals, but they just stay the same. and then I minus the off diagonal, so this becomes 1 over square root of 2, and this becomes minus 1 over square root of 2. So now I have to find the determinant of this matrix. So to do that, determinant of Q is equal to, so it's this times this minus this times this. So 1 over square root of 2 times 1 over square root of 2 minus 1 over square root of 2, 1 over square root of 2. And so I work through that. Let's see. Equals, this is just 1 over square root of 2 times 1 over square root of 2, so that's 1 over 2. So 1 over 2, and then the minuses cancel, so plus 1 over 2. So that actually just equals 1. So the determinant of Q in this case is 1, and the fact I picked Q as an orthonormal basis set is why this equals 1. And if you pick things as orthonormal basis sets, you're going to get that result over and over. But in general, you're not going to get the determinant of a matrix is equal to 1. And so now I have the determinant. 1 over the determinant is just 1, and so I've already solved for Q inverse. This is Q inverse here. Equals Q inverse, because this is a 1. 1 over 1 doesn't change anything. So now I have Q inverse. So now I need to find what x tilde is. So x tilde, which equals Q inverse times x, is going to equal 1 over square root of 2 minus 1 over square root of 2, 1 over square root of 2, 1 over square root of 2, times my x vector, which we found was the vector 2, 2. And so when I work that out, I get 2 over square root of 2 plus 2 over square root of 2. So that's going to equal 4 over square root of 2. And then I'm going to get minus 2 over square root of 2 plus 2 over square root of 2. So that's just going to equal 0. And then I can further simplify this if I want to by multiplying top and bottom by square root of 2. So I would have, well, there's just no point in that. We don't need to further simplify it. That's as good as any answer. So, so now I have this x represented with respect to this new basis. And just like we anticipated, it's all in the direction j1 and none in the direction j2. So we found how this same exact vector looks with respect to this new basis set. So it really makes sense based on the drawing that we had that we should have seen an answer like this. So now let's consider the function a equals 2, 0, 0, 1. So we have y equals a times x. And let's keep our same x. So this is going to equal 2, 0, 0, 1 times our x, which is 2, 2. And I do that math, and I get 2 times 2 is 4, 0 times 2 is 0, so 4, and then 2. So effectively, what is this function a doing? This function a is taking the first entry in my x, and it's multiplying it by 2, and it's taking the second entry in my x and leaving it unchanged. So that's how you can think about what this function is doing. So now I want to think about this function being mapped into this new basis set. So let's redraw this kind of picture. So here was our basis set 1, and then here was our basis set 2. I'll just draw a little 1 and 2. It's the same exact I1, I2, J1, J2 that we had before. And then we had this vector x here, x, and it equals 2, 2 when you write it with respect to the basis set 1. And it's mapping to this thing y, which is 4, 2. So let's draw our y vector like this. So this is y equals 4, 2. All with respect to basis set 1. These numbers, these are x and y with respect to basis set 1, right? So it's 2 over and 2 up, and then this becomes 4 over and 2 up. So now the question is, we've already seen how we write this vector x with respect to this basis set 2, and it's this, 4 over square root of 2. So 4 over square root of 2 in this direction, and then none in this direction. So how do we write this vector y with respect to that new set? Well, what we were going to try and attempt to do is actually rewrite our function a with respect to that new basis set to see if this actually pans out. So let's try and do that. So we know that our function, our new a tilde, should look like q inverse times a times q. So let's do that. We've already solved for Q. We already know Q and Q inverse. So if we do that, Q inverse becomes 1 over the square root of 2 minus 1 over square root of 2, 1 over square root of 2, 1 over square root of 2. And A is just 2, 0, 0, 1. And Q was 1 over square root of 2, 1 over square root of 2, minus 1 over square root of 2, 1 over square root of 2. And so I'll multiply these two matrices together first. So this is still 1 over square root of 2, minus 1 over square root of 2, 1 over square root of 2, 1 over square root of 2. And then I multiply these two matrices together, so 2 times this plus this times this. So I go through this math and I get 2 over square root of 2 here. I get a 1 over square root of 2 here. I get a minus 2 over square root of 2 here. And I get a 1 over square root of 2 here. And then I multiply those two matrices together, and I get 2 halves plus 1 half up here. And I get minus 2 halves plus 1 half here. And I get minus 2 halves plus 1 half here. I get 2 halves plus 1 half here. And then let's simplify that. And so I get 3 halves minus 1 half minus 1 half and 3 halves. So now I took this matrix A, this function A, 2, 0, 0, 1, and I mapped it to this new function A tilde, which is 3 halves minus 1 half minus 1 half, 3 halves. So I should be able to apply this function directly. So if I want to solve for y tilde, I just simply map my x tilde through A tilde, if this truly works. So 3 halves minus 1 half minus 1 half, 3 halves. And my x tilde that we computed was 4 over square root of 2, which let's simplify that. So that's 2 square roots of 2 by multiplying top and bottom by square root of 2 times 0. And then I work this thing out, and I get this vector 3 square root of 2 and minus square root of 2. So now I have y tilde. Now, we could have just gone directly, if this is true, and used this equation that y is equal to q y tilde. So if I do this now and I map this y tilde through q, I better get back the same y I got before. And the y I got before, when I did y equals ax, that y I got was 4, 2. So this better give me the same answer. So if I map x tilde through my new a tilde, then I better get, if I take this y tilde and map it through q, I better get the exact same y. But this y tilde was achieved through this x tilde a tilde. So let's just do this math and see if it actually pans out. So y tilde equals, so it's q, and so q is 1 over square root of 2, 1 over square root of 2, minus 1 over square root of 2, 1 over square root of 2. And our y tilde that we just computed was 3 square roots of 2 and minus square root of 2. And when I multiply those two together, I get 3 plus 1 and 3 minus 1. And then I get 4, 2. So I got the same y that I was expecting. So this actually works. So that's an example. I mean, I'm just crunching through the numbers, but this sort of procedure will just generally work. Okay, what do we need to note here? In my example, I presumed I moved from one orthonormal basis set to another orthonormal basis set, but it doesn't have to be that way. I could have, if I wanted to, I could have said, here's my original I1 and I2, and they're nice, they're length 1, they're perpendicular to each other, and I map them to a new orthonormal basis set. But I could have just said, I want to map to this basis set. I want to make J1 be exactly the same as I1. So it's this unit length vector here. And then for some reason I want to make J2 this vector. Sorry. Like this. They're not orthogonal. They're not perfectly perpendicular. And J2 is not length 1, but they're still a valid basis set because they're linearly independent from each other. So that's an important thing to remember. The last thing I want to talk about is the idea of being able to diagonalize a matrix. So this has to do with the eigenvalues of a matrix. So if you remember back to the eigenvalue eigenvector tutorial video, there was this idea that if you have a matrix that has all simple eigenvalues, meaning every eigenvalue it has is only of multiplicity 1. So if 2 is an eigenvalue, it only is an eigenvalue once. This is this idea. Then all of the eigenvectors are distinct. So let's imagine an A that's a 3 by 3 matrix. Okay. So if it's true about this distinct eigenvalues, then we have lambda 1 and lambda 2 and lambda 3. And each of these eigenvalues has a distinct eigenvector associated with it. Let's call that Q1, Q2, and Q3. And these eigenvalues aren't the same as each other, and the Q's aren't the same as each other. So not only are they not the same as each other, but they're linearly independent because they form this three-dimensional space. So let's go back to our eigenvalue-eigenvector equation. And what defines an eigenvector is we said if we take A times Q1, and Q1 really is an eigenvector, then we get back that same vector just multiplied by some constant that we call the eigenvalue. So I can write the same equation for all three of these. And if I do that, if you look at the way it ends up, let's first just write just this one equation, actually. So imagine if I load up this matrix with these columns. If I take this thing, so each of these things is a 3 by 1 thing, right? So blah, blah, blah. So this whole thing is a 3 by 3 thing. And if I were to take this and multiply it by this vector, lambda 1, 0, 0, then I would just get this exact equation. I'd have lambda 1 times, this is a 3 by 1 thing, so I have lambda 1 times Q1 and then all these other things times 0. So this is just an exact way to write this equation. But I can do this same thing 3 times. And when I do that, I'd get something like this. I'd say, well, I have AQ1 and AQ2 and AQ3 is equal to this matrix Q1, Q2, Q3 times this matrix lambda 1, lambda 2, lambda 3, sorry that's a 3, where these are all zeros. And so you can prove to yourself that this is true. I'm just basically recreating this example here, but I'm recreating it 3 times. So this is this big 3 by 3 matrix of the Q vectors. This is a 3 by 3 matrix. Each of these, 3 by 3 times a 3 by 1 is a 3 by 1 internally, so this whole thing is 3 by 3. So all the dimensions work out, and each of these is just recreating this. And when you look at that, because my eigenvectors are all linearly independent, and why are they linearly independent? Because they're distinct from each other with these eigenvalues. So they form a valid basis set, these eigenvectors, because any set of 3 linearly independent would be a valid basis set. So I can call this matrix here, I can call this some Q matrix, and it's this 3 by 3 matrix that is a valid basis set. It is invertible, and I can restructure this thing here as A times Q, and I can call this matrix here, let's call this matrix here capital lambda. So a capital lambda kind of looks like that. So I can rewrite this equation as AQ equals Q lambda, where lambda is a 3 by 3 matrix that's diagonal with the eigenvalues on its diagonal. And because Q is invertible, I can multiply both sides by Q inverse like this. Q inverse A Q equals Q inverse Q lambda. And then these become the identity matrix. So I've now solved for lambda is equal to Q inverse A Q. And so it turns out, I mean, think of what we've done here. We've taken a matrix A that the only thing we know about it is that it has distinct eigenvalues of multiplicity 1. And I've done a transformation, the same kind of transformations we've been talking about in this video. So I've pre and post multiplied it by some Q that's some basis set, and what it spits out to me is a diagonal matrix. And this is the diagonal matrix right here, a diagonal matrix with its eigenvalues on the diagonal. So when we boil this down, what this means is if I take a matrix A that has eigenvalues with multiplicity 1, what we say is we say that matrix is diagonalizable. And what diagonalizable means is it's similar to a diagonal matrix. So this equation here proves that A is similar to a diagonal matrix, and then just another way of saying that, similar to a diagonal matrix, is that it's diagonalizable. And in general, I mean, this is the way that you're going to have to remember this. So in general, if I have some A matrix that's an n by n matrix, and that matrix is diagonalizable, this is just directly equivalent. I mean, this is a one-to-one synonym for saying it has n linearly independent eigenvectors. So one is as good as saying the other. So if I tell you that A has n linearly independent eigenvectors, then you know it's diagonalizable, meaning it's similar to a diagonal matrix. And the same thing goes back and forth.